Real Money Fake Models, Deceptive Model Claims in Shadow APIs by Yig Zhang and colleagues at the CISP Helmholtz Center for Information Security. If you are running a machine learning pipeline right now, you absolutely need to hear this. Researchers are increasingly relying on shadow APIs. These are third-party services offering cheap, non-geo-blocked access to frontier models like GPT-5, Gemini-2.5, and DeepSeek. But a systematic audit of 17 shadow APIs reveals massive structural deception. The headline here is that 45.83% of evaluated endpoints completely fail fingerprint verification. You think you are querying a frontier model, but you are secretly getting substituted cheaper or older open source models. The impact is catastrophic. Performance drops by up to 47.21% on complex reasoning tasks. A Gemini 2.5 flash query might plummet from 83.82% accuracy on medical benchmarks down to just 37%. This bait and switch is actively corrupting AI research, affecting 187 academic papers in top venues like ICLR and CVPR, and wasting an estimated $140,000 in direct computing costs. Okay, let's unpack this. How exactly are these shadow APIs tricking researchers? How do we technically detect them? And what does this mean for the integrity of your ML pipelines? Welcome to this deep dive into the source material for AI Paper Podcasts.
Yeah, it's a massive supply chain vulnerability. And to really understand why these shadow APIs even exist, we have to look at the demand side first. Today, over 60% of natural language processing papers rely heavily on large language models.
Right.
But official APIs for these frontier models have incredibly strict geographical restrictions. OpenAI, for example, blocks direct access in regions like China, Russia, and Iran. And on top of that, enterprise pricing for these models is it's prohibitively high for many individual researchers or smaller academic labs.
Wait, so if enterprise pricing is the primary barrier, why not just run the smaller official open source models locally? I mean, why risk a gray market at all?
Because if you want to publish in top-tier machine learning conferences, places like AAAI, CVPR, or ACL, you need to demonstrate state-of-the-art performance, or at least benchmark your novel architecture against the absolute best models in the world.
You can't just use a small model.
Exactly. A local 7 billion parameter model just won't cut it for a baseline. So you have this huge volume of researchers, particularly in restricted regions, who essentially have no official way to access the frontier models they absolutely need to run their experiments.
And that pressure creates a massive gray market. Researchers turn to these shadow APIs for indirect access, treating them as a necessary bridge. And the scale of this problem is just staggering. The paper identified 17 major shadow APIs that have been utilized in 187 academic papers.
Yeah, it's everywhere.
And we aren't talking about obscure, unread journals here. 62% of these papers were accepted at top-tier peer-reviewed venues. The most popular shadow API they found has nearly 6,000 citations in the literature and over 58,000 GitHub stars. It is deeply embedded in the open source and research ecosystem.
What's fascinating here is the underlying infrastructure enabling this whole ecosystem. The researchers found that 11 of the 17 shadow APIs are actually built on open source model aggregators, primarily tools like OneAPI or NewAPI.
I've seen those on GitHub, but aren't they essentially just load balancers? How does a load balancer turn into a vehicle for deception?
Well, in theory, yes. They're designed to unify interfaces from various providers into a single standard OpenAI-compatible format. They handle API key management, secondary redistribution, and request routing. The problem is that from the user's perspective, they operate completely in the dark.
So you have no idea what's happening on the back end?
None at all. You send a request for GPT-5, but you have absolutely no visibility into where that request is actually being routed. Furthermore, from a compliance standpoint, it's a nightmare. 15 of these 17 services are run by individuals with zero verifiable provenance.
Wow.
Yeah, there is no transparent identity information, no corporate registration, nothing. You are blindly trusting an anonymous proxy with your research data and your computing budget.
If the infrastructure is this anonymous, it makes you wonder what's actually happening to the data when you hit send. And that is where the performance benchmarks come in. When you buy access to a frontier model, you are paying for a very specific capability, which is complex reasoning.
Right.
To test if users were actually getting what they paid for, the researchers benchmarked these shadow APIs against official baselines. They use standard EvilScope prompt templates across multiple difficult domains. We're talking AA 2025 for competition-level math, GPQA Diamond for PhD-level science, MedQA for medical diagnostics, and Legal Bench for law.
And the illusion of capability falls apart almost instantly on those benchmarks. It's essentially like paying for a Ferrari, but the dealers secretly swap the engine with a lawnmower.
That's a great analogy.
The chassis, the API response format looks right,
Yeah.
but the moment you hit the gas on a complex math problem, it stalls out. For example, Shadow API-A caused a 40% accuracy drop for Gemini 2.5 Pro and a nearly 39% drop for DeepSeek Reasoner on the AMA math benchmark.
A 40% drop is not a minor statistical variance. That is a completely different peer of model. And the medical benchmarks are where this gets genuinely alarming for downstream applications.
Absolutely.
On MedQA, the official Gemini 2.5 Flash model scores around 83.82% accuracy. But when querying that exact same requested model through the Shadow APIs, the accuracy plummeted to an average of about 37%.
Let's look at the specific failure modes because they tell a story. The paper highlights a concrete example regarding a complex question about perinatal HIV screening during labor.
Okay.
The official API correctly parsed the clinical guidelines, identifying the need for an HIV-1 and HIV-2 antibody differentiation immunoassay. It understood the nuance of the medical standard. The Shadow APIs, however, confidently and incorrectly recommended determining the genotype of the virus.
If you are an ML engineer building a clinical diagnostic tool using one of these APIs as your backend, that hallucination could be disastrous.
Terrifying.
And we see the exact same structural failure on LegalBench. They tested the models on highly specific legal applications like Rule 606B, which deals with the nuances of juror testimony.
Right.
The official API correctly noted that the rule bars testimony even for voir dire lies, meaning lies told during jury selection. The Shadow APIs completely hallucinated the legal reasoning, confusing the standard for a new trial with the standard for admissibility or citing completely unrelated habeas corpus rules.
It is a total collapse of domain-specific utility. But utility is the only thing that degrades. The safety guardrails completely shatter.
How did they test that?
The researchers tested these endpoints using Jailbreak Bench and Adva Bench. They threw various adversarial attacks at them, things like GCG or greedy coordinate gradient and base 64 encoding. In plain English, these are techniques that scramble or encode text to try and trick the model into bypassing its own safety filters. They then used a lightweight judge model to calculate a harmfulness score on the outputs.
I would assume the Shadow APIs just pass the request through, so the safety filter should remain intact, right?
You would think so. But the data shows these Shadow APIs act as wildly unpredictable black boxes. Because the back-end models are being secretly swapped or heavily altered, the safety responses are all over the map.
In what way?
Sometimes they drastically overestimate harmfulness and overly filter completely benign requests. Other times, they double the harmfulness score compared to the official API, completely failing to block toxic or dangerous outputs. You simply cannot guarantee the safety compliance of your application if your backend is routing through these services.
Here's where it gets really interesting. How did the researchers actually prove what was happening under the hood? It's one thing to see an accuracy drop, but it's another to prove a model has been swapped.
Exactly.
They used an active fingerprinting framework called LLMAP. At a high level, LLMAP queries a model with carefully crafted inputs and analyzes the output. It calculates the cosine distance of the linguistic patterns and structural features matching that accent or style against a massive reference database of known models. They ran this database on an NVIDIA DGX A100 cluster to process the fingerprints at scale.
The fingerprinting results are the smoking gun. Across 24 evaluated endpoints, 45.83% completely failed identity verification.
Almost half.
Yeah. The top one predicted model wasn't even in the same family as the claimed model. Another 12.5% showed massive cosine distance anomalies, meaning even if it matched the model family, the output distribution was heavily distorted.
So it's a literal bait and switch. Researchers paying premium rates for GPT-5 were actually being served GLM49B or DeepSeek v3, which are cheaper open-source alternatives.
Precisely, and it's particularly egregious for specialized models. DeepSeek Reasoner, for instance, is designed specifically to be a thinking model with advanced chain-of-thought capabilities.
Right, you want those reasoning tokens.
But the Shadow APIs were frequently just serving the standard non-thinking DeepSeek chat model. You are paying for intensive reasoning tokens that you are simply never receiving. Now, to be rigorous, the researchers didn't just rely on LLMAP. They ran a secondary independent check called MET, or Model Equality Testing.
For those who might not be deep into statistical testing, how does MET differ from the fingerprinting?
MET is a statistical two-sample hypothesis test. Instead of looking for a specific linguistic accent like LLMAP does, MET-T takes a large batch of outputs from the Shadow API and a large batch from the official API and checks if the underlying probability distributions match.
So it's a more mathematical approach.
Yes. If the Shadow API is serving the real model, The distribution should be statistically indistinguishable.
And did the two testing methods align?
They provided incredible independent confirmation. LLMAP and MET agreed 74.1% of the time with the Cohen's kappa, indicating substantial concordance. In plain English, two completely different auditing methods, one looking at linguistic style, the other looking at statistical probability, caught these APIs in the exact same lie.
That's fascinating.
But MET also helped uncover something really strange, which the researchers dubbed the Gemini anomaly.
Right, let's talk about the Gemini anomaly because this threw me for a loop. Remember that massive accuracy drop we discussed with Gemini 2.5 Flash on the MedQA benchmark, where it dropped from 84% down to 37%? Well, according to the data, Gemini 2.5 Flash actually passed the LLMAP fingerprinting tests. The cosine distance matched the official model.
The model identity was real.
But wait, you just said the accuracy dropped to 37%. If the shadow API is serving the actual real Gemini model, how does the complex reasoning completely collapse like that?
It points to a different, more subtle kind of structural deception. When fingerprint fidelity is high, meaning the model is the correct one, but behavioral consistency collapses, it suggests the shadow providers are aggressively manipulating the request pipeline to save money.
How so?
Think of it like hiring a brilliant mathematician, but putting them in a noisy room, taking away their scratch pad and giving them 3 seconds to answer. The mathematician is real, but the environment destroys their capability.
Oh, I see. So it's the settings, not the model itself.
Exactly. The providers might be using hidden prompt preprocessing, aggressively truncating the context window to save on token costs, or heavily misconfiguring inference parameters like temperature and top it to force faster, cheaper generation.
That makes perfect sense, especially when you look at the meta-information spikes the researchers documented. If you track inference latency, the time it takes for the model to respond, and token counts official APIs are highly stable.
Very consistent.
But the shadow API showed wild volatility. The coefficient of variation for latency in these shadow APIs was frequently more than twice the official baseline. You query the exact same model twice, and it takes wildly different amounts of time to respond. That variance absolutely proves unstable dynamic routing on the back end.
If we connect this to the bigger picture, we have to look at the economic incentives driving this entire ecosystem. The paper outlines 3 distinct grifts these shadow providers are running to extract money from researchers. The first is the information premium.
This is where they exploit the hype cycle, right?
Exactly. They charge a massive premium rate for a newly released, highly anticipated model, but secretly serve an older or slightly cheaper version from the same family.
Give me an example.
For example, a provider might charge 7 times the standard rate for Gemini 2.0 Flash, capitalizing on the demand for the newest version, but actually route the backend request to the older Gemini 2.5 Flash.
The second grift is discount substitution. This is the most brazen one. They charge you the official expensive parity rate for a true frontier model like GPT-5. You think you're paying OpenAI prices.
Right.
But they silently swap the backend to a completely free open source model like GLM-4. It is pure profit margin for the provider and a total loss of capability for the user.
And the third is the resale markup. In this scenario, the shadow provider charges the user a slight premium over the official rate, marketing it as a convenience fee for bypassing geoblocks, while still silently downgrading the backend model to an open source alternative to increase their margins even further on both ends.
The financial extraction happening here is remarkable. The researchers quantified this by analyzing over 1,000 GPT-5 queries, specifically on the GPPQA science benchmark. Users paid $14.84 for these queries, expecting official GPT-5 rates.
Well, what do they actually get?
Because the shadow API was secretly substituting cheaper models and truncating the token counts to save money, the actual computational value delivered to the user was only about $5.70.
Unbelievable.
The shadow provider pockets the difference, and the user gets a fundamentally degraded research output.
The downstream cost to the scientific community is what truly hurts. Let's just look at the 187 tainted papers identified in this specific audit.
Okay.
If researchers have to re-execute those pipelines to fix the identity inconsistencies and run their data through verified official APIs, it will cost between $115,000 and $140,000 in direct API credits and researcher time.
And that doesn't even account for the hidden rot in the literature. There are nearly 6,000 papers that cite those original 187 works.
Yes, the cascading effect.
If you are an ML engineer building a new methodology today, and you are basing your work on a baseline established in one of those tainted papers, your foundation is built on sand, you might be comparing your novel architecture against a supposed GPT-5 baseline that was actually generated by a much smaller, less capable open source model.
It artificially inflates your perceived progress and pollutes the entire academic ecosystem.
So what does this all mean? How do you secure your own ML pipelines if you are forced to deal with geographical or budget constraints and have no choice but to use a third-party aggregator? The paper lays out a very clear 4-stage auditor protocol.
Yes. Stage 1 is your first line of defense. You need to run 24 LLMAP probes against the endpoint.
So you fingerprint it right away.
Exactly. The paper states that if the cosine distance of the linguistic features exceeds 1.2 times the official baseline, you reject that API immediately.
If it passes stage 1, you move to stage 2, which is to run model equality testing with at least 500 samples. This ensures the statistical distribution of the outputs matches the official model.
Right. And if the null hypothesis of distributional equality is rejected, you walk away.
That sounds exhausting for a researcher who just wants to run a script. Is it really necessary to go through all 4 stages?
It is, because as we saw with the Gemini anomaly, passing the fingerprint isn't enough. That's why stage 3 focuses entirely on variance.
The latency and accuracy checks.
Exactly. You need to run at least 3 independent sessions on a held-out benchmark. If the standard deviation for accuracy across those sessions is greater than 5%, or if the latency coefficient of variation exceeds 0.15, you flag it. That variance is mathematical proof of dynamic model substitution and unstable back-end routing.
And finally, stage 4 is purely administrative, but crucial. You have to verify the provider's corporate registration.
In many cases, this means checking for an ICP filing, which is the mandatory internet registration system in China, where many of these open-source aggregators are based.
So if you are sending requests to an unregistered individual with no verifiable legal provenance, you are absorbing massive operational risk.
From a reporting standpoint, the community needs to adopt a strict pre-registration checklist. If your paper relies on LLM API queries, you should be documenting the exact endpoint URL, the pricing tier, the date of access, and ideally your LLMAP cosine distance in your methodology footnotes.
You have to prove the provenance of your data.
Exactly. Conference organizers and peer reviewers need to start treating unverified third-party API endpoints as a critical reproducibility risk, exactly like we treat unverified dataset provenance.
It is a massive wake-up call for the entire machine learning community. You have to verify your supply chain or your results mean nothing. We hope this analysis arms you with the protocols you need to protect your own work.
This raises an important question for all of us to consider. If a significant portion of the academic baselines and benchmarks we rely on to measure state-of-the-art progress were actually generated by secretly substituted cheaper models, how much of our recent algorithm progress is genuine and how much is simply an illusion created by a corrupted API supply chain?
It's a chilling thought to leave you with. Double-check your endpoints and think critically about the infrastructure powering your next big ML experiment. Thank you for joining us, and remember to subscribe to AI Paper Podcasts for more deep dives into the latest research. Keep building, but verify your backends.